All right, welcome back to the deep dive. Today we're diving into a paper with a title that'll really make you think. Path pooling. Train-free structure enhancement for efficient knowledge graph retrieval-augmented generation.
Yeah, that's quite the mouthful.
It is. But when we unpack it, what it's really about is how to make our LLMs, our large language models, a lot smarter.
Yeah.
And the paper's got this a really interesting way of looking at how we can use the connections between facts and get this all without any extra training.
Yeah, that's the really cool part. So this paper really tackles a core challenge in our field.
Okay.
It's all about LLMs, large language models, and how we can use knowledge graphs to make those LLMs way better.
Right.
So we want them to be more accurate. We want them to be more reliable. We don't want those weird hallucinations.
Right.
And we want them to have fewer of those gaps in knowledge.
Those gaps in knowledge.
This is becoming so important, as we're relying more and more on KGUI for real-world applications.
KGRAG, Knowledge Graph Retrieval-Augmented Generation.
Yeah.
We want these LLMs to give us good information, trustworthy information.
Precisely.
So it's really critical. And the way I kind of think about this is, imagine, you're trying to understand a complex topic, right?
Yeah.
And you've got two choices.
Mm-hmm.
You can either read a bunch of individual flashcards, or you can look at a concept map that shows you how all those flashcards fit together.
Yeah.
This paper is kind of like saying, hey, let's use that concept map.
Yeah.
Let's bring in that structure, the understanding of how everything connects, and let's use that to feed information to our LLMs.
Yeah, that's a great analogy. I think that really captures the essence of it. One of the things that's really exciting about this particular approach is its focus on efficiency.
Right.
And, the fact that it's train-free.
It's train-free. I love that.
Yeah, it's a big deal. So they introduced this technique called path pooling, which, cleverly incorporates the structure of knowledge graphs into these existing KG-RAG methods. And, a lot of these KG-RAG methods, they really focus on individual facts.
Okay.
And, the authors argue that a lot of the current approaches, they either don't really use the connections that are in those knowledge graphs, or they try to use them, but it gets really computationally expensive.
Oh, I see. So there's kind of a trade-off there.
Yeah, it's a trade-off. So path pooling offers this, very elegant alternative that's, lightweight and, really clever.
Okay, so path pooling, let's break it down. What is it actually doing?
So at its core, it's this train-free strategy that we can use to bring in that structural awareness that we want to these KG-ARG methods.
Right.
The ones that are just looking at individual pieces of information.
Right.
So they're looking at individual triples.
Triple, so that's the subject, relation, object?
Exactly, yeah.
Okay.
And the key to path pooling is this really cool idea called path-centric pooling operation.
Okay.
So imagine, we're looking at our knowledge graph and we're trying to find these important connection routes.
Okay.
Or, sequences of linked facts.
Okay.
And then we can use these routes to refine how important we think each individual fact is.
Oh, interesting.
So it's kind of like saying, hey, this fact is really important because it's part of this chain of understanding.
I see. So we're not just looking at facts in isolation.
Right.
We're considering how they fit into the bigger picture.
Exactly. And the paper actually does a great job of, starting by reminding us why this is so important.
Right.
So we know that LLMs are incredibly powerful.
Absolutely.
But their knowledge is bounded by their training data.
Right.
And that training data can be incomplete, outdated.
For sure.
And that leads to those inaccuracies that we talked about earlier.
Those hallucinations.
Exactly.
Okay.
So KG, or, the whole goal of KG-RAG is to overcome this.
Right.
It's like, okay, let's use these external knowledge graphs to give our LLMs more information.
Right.
And those knowledge graphs, they give us both the meaning of those facts, but they also give us the context of how those facts relate to each other.
That structure we were talking about.
Exactly, yeah.
Okay.
But as we touched on earlier, effectively using that structural context, that's really been a tough challenge in our field.
It has, yeah.
So the paper divides these existing KG-RAG methods into two main camps.
Okay.
So first we have path-based methods.
Path-based.
Yeah. And these methods, they try to retrieve entire connection routes from the knowledge graph.
Oh, wow.
So, they really want to leverage that structure fully.
Right.
But it can become computationally really overwhelming very quickly.
Yeah, I can imagine.
Yeah, it's like trying to map out every single possible journey on a massive transportation network.
Oh, yeah. That'd be a nightmare.
Yeah. And on top of that, a lot of these path-based methods, they require multiple back and forth interactions with the LLM.
Oh, so that's even more computationally expensive.
Exactly.
Okay, so it sounds like a bit of a double whammy with these path-based methods.
Yeah, exactly.
So what's the other approach?
So the alternative is what we call triple-based KGRAG.
Triple-based, okay.
Yeah. So instead of retrieving whole paths, they focus on those individual triples.
Right, those subject, relation, object units.
Yeah, exactly.
Yeah.
And this is much more efficient.
Okay.
Often, they only need one interaction with the LLM.
Oh, wow.
But the downside, the trade-off here, is that structural information that we talked about,
Yeah.
it often ends up being treated as less important than the meaning of the individual facts.
Oh, I see. So they kind of miss the forest for the trees a little bit?
Yeah, that's a good way to put it.
Okay,
Yeah.
okay.
So some methods, they'll try to encode some structural hints, but it's not as comprehensive as if you're looking at those whole paths.
Right.
A really good example of this is subgraph RAG.
Subgraph RAG, okay.
Yeah, so subgraph RAG uses a neural network for really efficient triple retrieval.
Okay.
And it actually does try to incorporate some structural features.
Okay, so it's kind of a hybrid approach in a way.
Yeah, in a way.
Okay, so it sounds like we've got this fundamental trade-off, right?
Yeah.
Triple-based is fast, but it might miss that bigger picture. And path-based gets the context, but can be really slow and resource intensive.
Exactly.
Okay.
And this brings us to the central question that the paper is asking.
Okay, what's that?
Can we find a way to harness the power of that structure in knowledge graphs?
Okay.
In a way that's low cost, train-free,
Right.
but still operates within that efficient triple-based framework.
Okay.
So can we get the best of both worlds?
Right. And that's where path pooling comes in. Okay, so tell me more about that.
So path pooling, it's their solution to bridging this gap.
Okay.
And it's got two main steps.
Okay.
The first step is what they call searching path kernels.
Searching path kernels. Okay.
So you can think of this as, finding those important connection routes.
Okay.
So they take those triples that have already been retrieved,
Right.
using a standard triple-based method,
Okay.
and they build a small subgraph from those triples,
Okay.
and then they use graph search algorithms,
Okay.
like Dijkstra's algorithm,
Dijkstra's algorithm, all right.
to find these significant paths that originate from the entities in the original question.
Oh.
So they really prioritize those shorter paths,
Okay.
for efficiency, and also to prevent what they call over-smoothing.
Over-smoothing. What's that?
That's when the signals from those distant parts of the graph, they kind of become too mixed.
Oh, I see.
Yeah. And if a triple isn't part of those identified paths, they just treat it as, a single-step connection.
Oh, okay. So it sounds like they're not searching the entire massive knowledge graph for these paths. They're just looking within that smaller set of relevant triples that they've already pulled out.
Exactly. Yeah.
Which makes sense. I mean, that sounds way more practical.
Exactly. So that's the first step.
Okay.
And then the second step is what they call smoothing along kernels.
Smoothing along kernels.
Yeah. So once they've identified those key paths,
Yeah.
Those kernels,
Right.
they apply the average pooling operation
Okay.
to the important scores of the triples that lie along those paths.
So it's like the importance of a fact is kind of being influenced by the importance of the facts that it's connected to in these key routes.
Precisely.
Okay.
And this really helps to propagate that structural information.
Right.
Without needing any additional training.
Which is fantastic.
It is, yeah. And they also introduce this, what they call a positional score.
Positional score. Okay.
Yeah. And that's based on where a triple appears in a path.
Okay.
So it's kind of preserving some of that sequence information.
I see.
Yeah. And then finally, if a triple appears in multiple important paths,
Yeah.
they take the highest score
Okay.
from any of those paths.
So if it shows up in multiple key connections, it gets a stronger signal.
Exactly.
Yeah, that's interesting.
Yeah, so it's like reinforcing the importance of that fact.
Right.
And then the paper goes on to discuss two ways they use these, affined triple scores to actually boost the overall KGRAG performance.
Oh, cool. So they're actually putting this into practice.
Yeah.
Okay, what are the two ways?
So the first way is what they call position re-ranking.
Position re-ranking, okay.
Yeah. So we know that LLMs, they often pay more attention to information that's presented later in the input.
Right, the recency bias.
Exactly, yeah.
Okay.
So what they do is they reorder the retrieved triples based on their smooth scores. and they put the more important ones closer to the final question.
Oh, so they're kind of working with that known tendency of LLMs.
Exactly, yeah.
That's clever.
It is. And then the second way is what they call triple reselection.
Triple reselection.
And this is a two-step process.
Okay.
So first they make a broad selection of, the top K triples
Okay.
using a standard triple-based KGOG score.
Okay.
And then they apply their path pooling scores to those top K triples
Okay.
and narrow it down to a smaller set
Right.
of top K triples.
Okay.
And then that refined set is then ordered again using that same recency bias.
Right. Right.
So the idea here is to first get a good set of relevant facts
Yeah.
and then use the structural information from path pooling to kind of fine-tune that selection.
I see. So it's like a first cut based on general relevance and then a second cut based on that structural information.
Exactly.
Okay. Yeah.
And to really see how this works in practice, they tested it on this challenging data set called CWQ.
CWQ.
Okay. Which is designed for questions that require reasoning over multiple pieces of knowledge
Wow.
from a large knowledge graph called Freebase.
Freebase.
Yeah. And they used standard metrics for these types of tasks.
Okay.
Macro F1 and hit it in one.
Right.
And they compared their path pooling approach,
Yeah.
integrated into that state-of-the-art triple-based method subgraph RAG
Okay.
against the original subgraph RAG.
Right.
And they did this using, several different open source LLMs,
LLMs. Okay.
including various sizes of Llama and Qwen.
Llama and Qwen.
Yep.
Okay. So what did they find? What were the results?
Well, the results were pretty compelling.
Okay.
So they found that both their re-ranking and reselection methods, when combined with path pooling, they consistently led to better performance
Oh, wow.
across all those different language models
Okay.
and with different numbers of retrieved triples.
Oh, interesting. Yeah. So what's really impressive is that, across the board,
Yeah.
it didn't matter if they used smaller LLMs or larger LLMs, or even LLMs from different families.
Right.
Path pooling always delivered these, significant performance boosts.
Oh, that's amazing.
It was, yeah. And one of the things that was really cool was they showed that using reselection with even a small number of triples,
Okay.
let's say 25,
Okay.
enhanced with path pooling,
Right.
could actually outperform the original subgraph RAG
Wow.
using a much larger number of triples, like 200.
So using less information but better selected information actually led to better performance.
Exactly.
That's fascinating.
Yeah. And it really highlights those, efficiency gains that they were talking about.
Absolutely, because it seems like it's not just about the quantity of information, it's really about the quality and how well it's connected.
Exactly.
Okay. So they saw these great results. Did they do any further analysis?
Yeah, they did. They looked at the impact of using different graph search algorithms
Okay.
for finding those important connection routes.
Right.
So they compared, Dijkstra, breadth first search, BFS,
Yeah, Vest.
and random walk.
Okay.
And all of them, they showed some improvement,
Yeah.
but random walk performed the worst.
Oh, interesting.
Yeah, and that's probably because of its, random nature.
Right. It might miss some important structural links if it's just randomly going through the graph.
Exactly.
Okay.
And BFS and Dijkstra, they showed similar performance,
Okay.
but Dijkstra was, significantly more computationally efficient,
Oh, okay.
especially as the number of triples increased.
Right. Which makes sense.
Yeah, and that's, really important for real-world, large-scale knowledge graphs.
Absolutely. So it seems like Dijkstra was kind of the sweet spot there, right?
Yeah, it provided that, best balance of effectiveness and efficiency.
Right.
They also experimented with, different pooling strategies.
Okay.
So they compared average pooling.
Right. Which is what they used in their main method.
Exactly.
Right.
They compared that with max pooling.
Mac and pooling. Okay.
And they found that average pooling consistently performed better.
Oh, interesting.
Yeah, and they think that that's because average pooling does a better job of keeping the neighborhood information
Okay.
along those paths.
So it's not just about the single most important fact. It's about kind of the collective importance of a connected set of facts.
Exactly.
Okay. And max pooling just kind of takes the single highest score.
Yeah,
And it might miss some of that influence from the other connected facts.
precisely.
Okay.
And then finally, they did a little deeper dive into that positional bias of LLMs.
Okay.
So they explored this strategy called lost in the middle,
Lost in the middle.
where, high scoring information,
Yep.
it's placed at both the beginning and the end of the input sequence.
Oh, interesting.
Yeah. And they found that both their recency bias approach
Right.
and this lost in the middle strategy, they both improved results
Okay.
with some slight variations depending on the LLM.
Right.
But they recommend sticking with the recency bias approach
Okay.
just because it's, simpler and more robust.
Okay, that makes sense. So can we just take a step back and summarize what this paper's all about?
Yeah, for sure.
What are the key takeaways here?
So, at a high level, this paper introduces path pooling.
Path pooling.
Which is this really clever and efficient way to bring in that structural information from those knowledge graphs into these, fast, triple-based KGR methods.
Right.
And the beauty of it is it doesn't require any additional training.
I love that.
Yeah. So they achieve this by, first identifying those important connection routes within those retrieved facts.
Okay. And then using those routes to kind of fine tune the important scores of the individual facts.
Right. So like we were talking about, it's not just looking at the facts in isolation. It's really understanding how they fit together.
Exactly.
Okay.
And then they can use those enhanced scores to either reorder the facts or to select a smaller set of more important facts.
Right.
Before they feed them to the LLM.
Okay.
And this leads to, some really significant improvements in those knowledge-intensive tasks.
That's amazing. And, to put this into, the broader context of research in this area, early work in KGO really focused on those path-based approaches.
Yeah, they really emphasized that graph structure.
Right.
But, that computational cost was a major bottleneck.
Absolutely.
And so that led to this movement towards those more efficient triple-based methods.
Right.
But the challenge has always been, how do we bring back some of that structural awareness without, sacrificing efficiency?
Right.
Or, introducing the complexity and expense of training these really intricate embedding models.
Right.
And so this paper, it offers this really elegant and lightweight solution.
Yeah, it sounds like a really nice contribution to the field.
Yeah, it is.
Okay, so now for my favorite part of the show, the novel notions segment.
Yeah.
Based on this paper, what kind of interesting follow-up research could we imagine?
So one really interesting direction, I think, is, to explore using more sophisticated but still train-free graph algorithm for that initial step of finding those important connection routes.
Right.
So the paper used, shortest paths with Dijkstra. And they also looked at, BFS and random walk.
Right.
But what if we considered, algorithms that can identify a more diverse set of paths?
Oh, interesting.
Yeah. Or perhaps paths that go through, particularly influential nodes within that subgraph.
Right.
Maybe using, measures of node centrality or betweenness.
So instead of just the most direct routes, we might look for routes that go through these key hubs of information.
Exactly, yeah.
Okay.
And the hypothesis here would be that these, more nuanced structural insights, they could lead to even greater performance gains with path pooling.
Oh.
So you can imagine researchers comparing various, graph traversal and pathfinding algorithms.
Right.
And really analyzing their impact on, both the effectiveness and the efficiency of the overall KG Audiage system.
That's really cool. So it sounds like, building on this paper's findings, there's a lot more we could explore in terms of the types of structural information we're capturing.
Yeah. Okay.
And how that impacts performance.
Yeah. And, I think it'd be really valuable to see if, algorithms that capture different aspects of that graph structure,
Right.
Maybe those that are less susceptible to local biases or better at handling sparse graphs,
Okay.
could offer advantages for, specific types of knowledge-intensive questions.
It's interesting. So different types of questions might benefit from different path search strategies.
Exactly.
Okay. That's a really cool research direction. So what's another avenue we could explore?
Another really interesting one is developing what we call adaptive path pooling strategies.
Adaptive path pooling. Okay.
Yeah. So the current method, it uses these fixed parameters
Okay.
for the path kernel search
Right.
and for the smoothing operation.
Right.
But what if we could dynamically adjust those parameters
Oh, okay.
based on the specific query
Right.
or
Yeah.
even the characteristics of the initially retrieved triples?
So the system could kind of analyze the situation and decide how aggressive it needs to be with the path pooling.
Exactly.
Okay.
So, researchers could explore developing metrics to assess the initial quality
Yeah, okay.
and the structural coherence of those triples that are retrieved by that baseline KGR method.
Right.
So if that initial retrieval, if it seems strong and well connected,
Yeah.
maybe a less aggressive smoothing or a more restricted path search, that would be optimal.
Okay.
But if those initial triples are, more scattered
Right.
or they have lower confidence scores,
Okay.
then maybe a more extensive path search and stronger smoothing would be better.
Right. Right. So it's kind of tailoring the approach to the specific situation.
Exactly.
Okay.
And this could even involve developing a, lightweight meta model,
Okay.
maybe a small neural network
Okay.
that takes, features of the query and those initial retrieved triples as input,
Okay.
and then predicts the optimal path pooling parameters for that specific instance.
Oh, wow.
Yeah. So this actually connects to that broader area of, uncertainty estimation
Okay.
in both LLMs and RGG systems.
Right. Right. So it's kind of like understanding when the initial information might be less reliable
Exactly.
and then adapting the augmentation strategy accordingly.
Exactly.
Okay. Okay. Those are both really interesting research directions. Well, it looks like we're coming to the end of our deep dive.
Yeah.
So to wrap things up, this paper on path pooling, it presents this really promising, efficient, and again, train-free technique
Yeah.
to significantly improve KGRA
Yeah.
by really intelligently leveraging the structure within those knowledge graphs.
Precisely.
And, the simplicity and effectiveness of this approach, it really makes it a noteworthy contribution to our field.
Absolutely.
It's just really elegant.
Yeah, it is.
And it makes you think, as knowledge graphs continue to evolve and LLMs become even more sophisticated,
Yeah.
what other, really ingenious low-cost techniques are we going to discover
Yeah.
to really bridge that gap between structured knowledge and neural processing?
Yeah. It's a really exciting area of research.
It is. It is.
And this paper really provides, a solid foundation for, future exploration.
Definitely a lot to consider. Well, for those who want to delve deeper into the specifics of the paper, you can find the link in the description below.
Yeah.
And thanks for joining us on the deep dive for this, look into cutting-edge machine learning research.
Yeah.
Until next time, keep those models learning.
Keep them learning.